Now that we have discussed the variables temperature and pressure, let's discuss the third meteorological variable, water vapor. Water vapor is important for air quality forecasting because it can increase production of secondary PM2.5, including sulfates and nitrates in some areas of the country. In addition, when water vapor condenses into precipitation, it can increase deposition of pollutants. So therefore, forecasters are interested in changes in water vapor content both temporally, such as how does the diurnal relative humidity profile change, and vertically, so that we can predict if or at what level clouds may develop. So where does the water vapor in the atmosphere come from? Let's review the water cycle. As we know, most of the Earth is covered by water. The oceans are the major source of water vapor in the atmosphere through evaporation. However, there is also some evaporation from vegetation over the land surfaces and from snow and ice pack. Once the water evaporates into the air, it is stored in the atmosphere as water vapor. Some of this water vapor condenses into clouds. When the cloud droplets get large enough, they fall as precipitation. The water then makes its way back to the ocean through groundwater runoff. So how do we evaluate water vapor content for forecasting? There are two parameters we look at: dew point temperature and relative humidity. Dew point temperature is the temperature to which a given parcel of air must be cooled in order for saturation to occur. And this is something that we can measure directly through instruments at all the surface weather observation stations around the country. However, relative humidity is the term that most people are more familiar with. This is a measure of how close the atmosphere is to being saturated. This is a parameter that we derive from temperature and dew point temperature. When dew point temperature equals the air temperature, saturation is reached and relative humidity equals 100%. If relative humidity is 100%, then the air is saturated and condensation occurs. In other words, the water vapor that is in gas form will condense and form a liquid droplet. And this can occur in the form of clouds or fog. We can also see this phenomena when we have dew or frost on the grass in the morning, and even sweating on a glass on a hot day. Relative humidity is the ratio of actual water vapor content in the air to the total water vapor capacity of the air. In other words, it tells us how close an air parcel is to being saturated. Like we said before, a saturated air parcel will have a relative humidity of 100%. However, if an air parcel only contains half the water vapor it can possibly hold, or half its capacity, its relative humidity will be 50%. Since relative humidity depends on water vapor content and capacity, you can change relative humidity by changing either one of these parameters. The dew point temperature tells us the actual water vapor content of the air parcel. For a given air mass, it remains relatively constant throughout the day, so water vapor content is fairly constant. The air temperature tells us the water vapor capacity of a given air parcel. Warmer air has greater water vapor capacity than cold air. Unlike dew point temperature, air temperature does change during the day, thus changing the water vapor capacity. As we can see in this example, at night the air temperature cools, so the capacity decreases. Therefore, the relative humidity increases. On the other hand, during the day, the air temperature increases, the capacity increases, and therefore the relative humidity decreases. So where do we get the moisture information from our surface observations? Well, once again, we're going to look at our surface station plot that we have already discussed when talking about temperature and pressure. And now we can see in the lower left corner of the plot, we can see the dew point temperature value. In this example, it is 63 degrees. When we're coming up with a forecast, there are a multitude of products available that can give us information about both relative humidity or dew point temperature. This is an example showing a spatial relative humidity forecast plot where you can see the different relative humidity levels are color-coded to make it easy for you, the forecaster, to determine if it's a widespread high humidity event or if it's something very localized. This is very important to consider, especially if your forecast area has a lot of changes in topography where you can get very localized areas of high or low relative humidity. In addition to looking at spatial forecasts of moisture parameters, we can get these same parameters available for a point-specific location, such as your forecast city. This is an example showing a meteogram of forecasted temperature, dew point temperature, and relative humidity by hour for the next 48 or 72 hours. As you'll see in the top portion of the plot, where temperature and dew point temperature are shown in the same graph, where the dew point and temperature are further apart, on the corresponding graph in the third bar, the relative humidity is lower. On the other hand, when we get further out in time, where the temperature and dew point temperature are very close together, the relative humidity increases. So now that we've talked about these moisture parameters at the surface, we can also measure these things aloft. If you'll recall from the temperature section, we briefly introduced vertical temperature profiles as measured by weather balloons. The weather balloons also measure dew point temperature, so we can see how the moisture content varies vertically in the atmosphere. And once again, we will get into more detail about reading this type of plot in later sections of this course. For now, I just want to show you that you can see rapid changes with altitude in the dew point temperature. Some layers have much drier air and some layers have much moister air, higher relative humidity, because once again, we can use the temperature line and its relative proximity to the dew point temperature line to estimate the relative humidity of the air. So now that we've covered all the different meteorological variables, let's do a quick recap of what we've learned in these sections. Temperature affects PM 2.5 formation, emissions, dispersion, and transport. Specific examples would be that lower temperatures can result in more home heating, which can be higher energy production and secondary pollutants formed from that, or more direct emissions from residential wood burning. Higher temperatures will promote more volatilization of VOCs and increase biogenic emissions. Pressure is important because it controls wind speed and direction, which influence pollutant dispersion and transport. Large pressure differences lead to stronger winds and increased dispersion, while small spatial pressure differences contribute to stagnant conditions. And finally, water vapor can increase the production of secondary PM 2.5, including sulfates and nitrates. So what's next? The following sections will cover meteorological phenomena, including large-scale pressure patterns, regional and local winds, fronts and air masses, stability and mixing, and clouds, fog, and precipitation.